All right, so here are the notes for section 10.1, which is the probability. So here we got sample spaces and the probability functions. So example 1, find the probability of each of the events. Tossing 2 heads in a row on two tosses, of a fair coin. So sample space is just kind of the list of all possible outcomes. So if I toss a fair coin twice, I could get tails, tails, heads, tails, tails, heads, or heads, heads. So 2 heads in a row is 1 out of the 4 possible options. So if we're drawing a queen from a standard deck of 52 cards, well, there are 4 queens in the 52 cards, so the probability is 1 out of 13. Rolling a sum of 4 on a single roll of 2 fair die. Okay, so let's see here. So if I'm rolling 2 die, there are a total of 36 possible outcomes, 6 from the first dice, 6 from the second dice. Rolling a sum of 4, well, let's see how we can do that. We can do it a 1 and a 3, we can do a 2 and a 2, and we can do a 3 and a 1. So that gives us a 3 out of 36. Notice that 1 and 3 and 3 and 1 are different things because first die, second die. Here it doesn't matter because they're both 2s, which would be, what, 1/12? So 1/12. All right, having tendinitis, if your doctor tells you that further tests are needed to determine if your sore knee is caused by tendinitis, bursitis, arthritis, or a torn meniscus. This can't be done if you don't know the relative likelihoods of each. So, is tendinitis super common and is a torn meniscus super rare? Because without knowing that information, we can't make a decision. Okay, so in here, we got probability of event. I'm assuming equally likely outcomes. So if E is an event in a finite non-empty sample space, meaning you don't have an infinite number of possibilities, of S equally likely outcomes, then the probability of the event E is given by the number of outcomes E divided by the number of in E, so the things you are looking for divided by the total number of outcomes. So like up here, there are 4 possible outcomes. We are looking for 1 of them. So, all right, find the probability of rolling a sum divisible by 3 on a single roll of 2 fair die. So let's see here. So once again, there are 36 total outcomes. Let's see here. So, divisible by 3, huh? All right, so the numbers that are divisible by 3. So we're going to roll. We could have a roll of 3. We could have a roll of 6. We could have a roll of 9. We could have a roll of 12. So we need the individual likelihoods of each. So to roll a 3, there's 2 ways to do that: 1 and 2, 2 and 1. To roll a 6, there's 5 ways to do that: 2 and 3, 3 and 2, 1 and 5, 5 and 1, 3 and 3. To roll a 9, there are 4 ways to do that: 5 and 4, 4 and 5, 6 and 3, 3 and 6. And to roll a 12, there's only 1 way to do it. So the overall likelihood of that happening is the total probability. So 2, 7, 8, 9, 10, 11, 12. 12 out of 36, which is 1/3. So I have a 1 in 3 chance if I roll 2 dice, the number is divisible by 3. Okay, so here we've got a probability function. Probability function is a function P that assigns real numbers to each outcome in a sample space subject to the following conditions. The probability of every outcome lies between 0 and 1. 0 meaning it will never happen. 1 is guaranteed to happen. So you can't be more than 100% sure something will happen, or less than 0% sure. The sum of all the probabilities is 1, meaning that one of the events has to happen. And the probability of the empty set of nothing happening essentially is 0. Okay, outcomes not equally likely. So let S be a finite, non-empty sample space in which every outcome has a probability assigned to it by a probability function P. If E is any event in S, the probability of event E is the sum of the probabilities of all the outcomes contained in E. So example 3, prior to the Final Four basketball tournament, the sports analyst considers the strengths and weaknesses of the 4 remaining teams and suggests a probability distribution shown for the chance of winning the championship. Determine whether the distribution is valid. So each individual probability has to be between 0 and 1, which those all are. The sum of the probabilities has to be 1, so I need to check that 2/5 plus 1/3 plus 1/6 plus 1/8 is equal to 1, and if it's not, then it can't be a probability. That's the second rule. So I'm going to grab a calculator. 2/5 plus 1/3 plus 1/6 plus 1/8. So if I add those up, I get 41 out of 40, which is not equal to 1. So this is not a valid distribution. The likelihood of all the events occurring is more than 1, and that can't happen. Okay, so determining probabilities here. So determine the sample space of all the possible outcomes. Choose outcomes that are equally likely, so like dice rolls, coin flips. If the sample space has equally likely outcomes, so probably event E is determined by the number of outcomes in E, so the number of ways to do the thing you want to do, divided by the total number of outcomes. If the sample space does not have equally likely outcomes, determine the probability function. This is not always easy to do. Check to be sure the conditions are met. Then the probability of event E is by adding up the probabilities of all the outcomes contained in E. All right, so example 4. Sal opens a box of a dozen chocolate-covered creams and generously offers 2 of them to Val. Val likes vanilla creams the best, but all the chocolates look alike on the outside. If 4 of the 12 creams are vanilla, what is the probability that both of Val's picks turn out to be vanilla? So let's see how many ways that. So first, we need to figure out how many different ways she can pick those 2. So we've got a dozen chocolate chip cookies, or not chocolate-covered creams, so 2 out of 12. Whoops, no other way. 12 total. I need to pick 2 of them. So that comes out to be, let the calculator handle it. 12 choose 2 is 66. There's 66 different ways Val can choose that. So that's the number on the bottom. The number on the top is the number of ways that she can choose the 4 vanilla creams. So that would actually be out of the 4, she has to choose the 2, which is 6. So there's 6 different ways that she could choose. If there are 4 of them and she has to pick 2 at a time, which means that there is a 1 in 11 chance that she will pull this off. So the number of ways that she can make the selection she wants, there's 4 creams, she needs to choose 2 of them, divided by the total number of ways. There's 12 total candies, she has to choose 2 of them. Okay, multiplication principle. Suppose event A is probability P1, event B is probability P2. Under the assumption that A occurs, and the probability of both of them occurring is just the product. So when things happen in sequence, you multiply them together. All right, so according to the American Red Cross, the distribution of blood types in the U.S. population is 45% type O, 40% type A, 11 type B, and 4% type AB. If 2 people are chosen at random, find the probability that both have type O. Well, 0.45 for the first person having O times 0.45 for the second person having O. So 0.45 times 0.45. There is a 0.2025 probability that both of them selected have type O. Neither has type A. Well, type A is 11%, which means not having type A is 89. So 89 times 89. Oh no, type A is 40%. So it'd be 0.6 times 0.6. Sorry, I was going backwards. So 0.6 squared is 0.36. Probability that neither of them has type A. Both have the same blood type. Okay, so this is a bit tricky. We have to do double O, double A, double B, double AB, and add them up. So double A be 0.45 squared. Double O, double A, double B, double AB. So 0.45 squared plus 0.4 squared plus 0.11 squared plus 0.04 squared. So 0.3762 would be the probability that they both have the same blood type. All right, Venn diagram. So this is where you have the circles that overlap. So example 6 here, Pascal High School, 54% of the students are girls and 62% of the students play sports. Half of the girls at the school play sports. What percent of the students who play sports are boys? Okay, so let's see here. So let's just draw a lovely Venn diagram. So here's all of the students. We have some girls, we have some boys. 54% of the students are girls. So these two sections will make this part the ladies, this part the boys. So I should draw my picture bigger. So this is 0.27, 0.27, because half of them play. 62% of the students play sports. Whoops, actually, sorry, this is sports over here. So if I know 0.27 of the girls, so 62 minus 27, means that this piece is 0.35. So 0.27, 1 minus 0.27, minus 0.27, minus 0.35, means that the outside is, so here's girls who play sports, students who play sports, which means this outside piece is, this is boys who play sports, and that's just boys. Okay, or boys who do not play sports. This would be boys that do play sports. What percent of the students who play sports are boys? Well, if 62% of the students play sports and 0.27 of that is girls, the other part is the what percent of the students who play sports are boys? Oh, whoops. So 0.35 divided by the total number of percent that plays boys or play sports. So the 0.35 out of the entire sports circle. So this is about 56.5%. If a student is chosen at random, what's the probability that this student is a boy who does not play sports? That's that chunk there. So 11%. So girls in the school, girls who play sports. This is students who play sports who aren't girls, so we'll call that boys. And then outside, it does not fall in either of these groups. So if that's girls who play sports, boys who play sports, the only thing left is boys who do not play sports. Okie dokie. Additional probability. So events in A and B, if either of them can happen, you sum up the likelihood, and if there's some overlap, you have to subtract off that overlap. This controls for double counting. This happens a lot, like if you're doing a deck of cards, like what's the probability of drawing a red card or a queen? Well, there's 26 red cards, 4 queens, but you have to subtract off the 2 red queens because otherwise you're counting them in both categories. If A and B don't intersect, that means that this part goes away. Those are exclusive events, like flipping a coin and getting heads and tails. Like you can't get both at the same time. They're exclusive. Drawing a black card or a red card, exclusive. Drawing a 2 or a 7, those are exclusive. Example 7, Pascal High School, 68% of the students have cell phones, 77% have an iPad, and 62% have both of them. What's the probability that a student has a cell phone or an iPad, but not both? All right, so let's see here. So let's draw our lovely Venn diagram. So over here, so 68% have a cell phone, 77 have an iPad, and 62% have both. So this little chunk in there has to be 62, that's the both. So let's see here, we'll call this cell phone, we'll call this iPad. So cell phone, if 62% is already covered here, this has to just be 6%, which means this is over here 15, because 77 have an iPad, so these numbers have to add up to 77. So our total we have left is 100 minus 6 minus 62 minus 15. So there are 17% of the students have neither cell phone or an iPad. So let's see here. Cell phone or an iPad. So we do cell phone, which is 68, plus iPad, 77, minus the students that have both, because otherwise we are double counting, and that ends up being more than 100%. So 68 plus 77 minus 62, So 83% of the students have either a cell phone or an iPad. The other way to do it is be 6 plus 62 plus 15. You only count that section once. Cell phone, iPad, both. These both would qualify for the or. Cell phone or an iPad, but not both. Okay, so that would just be these two, 6 plus 15. So having only a cell phone, only an iPad, that would be 21%. Okay, tree diagrams, 2 identical cookie jars on the counter. Jar A contains 2 chocolate chip and 2 peanut butter cookies. Jar B contains 1 chocolate chip cookie. I feel like I'm missing something out of that. Nope. We select a cookie at random. What is the probability that is a chocolate chip cookie? Let's see here. So, let's... okay, so jar A has chocolate chip, chocolate chip, peanut butter, PB. Jar B has only chocolate chip. Now you wouldn't want to say 3 out of 5, but that's not quite true because this is 2 out of 4 if you are in jar A and 1 out of 1 if you pick from jar B. So let's see here. You have here, come back out here. So you're standing here making your choice. So you have a 50% chance of picking A. You have a 50% chance of picking B. This is 1 because if you pick B, you're guaranteed this. So the probability of getting a chocolate chip cookie here is 0.5. Up here, there are 4 choices. So if I'm selecting at random, each of these individual choices has a 1/4% or 25% chance of occurring. So that means to get this chocolate chip cookie, I have to multiply those 2 things because I have to have selected jar A and, so this is 0.125. These are actually all 0.125. So the total likelihood of selecting a chocolate chip cookie is this one and this one and this one. So 0.125 plus 0.125 plus 0.5. Which comes out to be 0.75 or a 75% chance. Which if you just do 3 out of 5, that's actually only 60%. Okay, conditional probability. Probability of drawing a chocolate chip cookie in example A is an example of a conditional probability because the cookie probability depends on the jar outcome. Symbol uses the bar here, P of A given B, meaning the probability of an A given a B occurs. So probability of A and B is equal to the probability of A times the probability of B given A. So Sal opens a box of a dozen chocolate-covered creams, and Janice offers 2 of them to Val. Val likes vanilla cream the best, but all the chocolates look alike on the outside. 4 of 12. What's the probability that both happen? So let's see here. Okay, so the other way we can do this is they just think about in terms of draws. So her first draw, there are 4 vanillas out of the 12. The second one, so that's P of A, probability of getting 1. P of B given A means that the next time I draw, there's now only 3 vanillas with 11 left over. So this is 12 out of, I'll do that in my head, 132, which reduces to our previous answer of 1/11. So conditional probabilities mean that the second probability has changed depending on the first. That's an example of what's not independent events. Events A and B are independent if the likelihood of B occurring given A is the same thing as if B has just occurred by itself. So the A has no effect on the probability of B, which means it's just a product. Now these events are dependent because my likelihood of selecting a second vanilla cream depends on whether I got one the first time. Because if I got one the first time, there's 1 fewer to choose, and there's 1 fewer total candy to choose from. So here's the lovely probability. If the event B depends on the event A, then the probability of B given A is the probability they both occur divided by the probability of A. Okay, so example 10. Suppose we have drawn a chocolate chip cookie at random from one of the jars described in 8. Given this chocolate chip, what's the probability that it came from jar A? So probability that it came from jar A, given that, we know that is a chocolate chip cookie. So on top, probability that it is jar A and chocolate chip divided by the probability of chocolate chip. Now notice that these are the same. So let's see here. The probability, so A and B means we multiply. So the probability of jar A, we had a 1/2 chance of getting that. The probability of selecting a chocolate chip from bar A is 2/4. It's 2 out of the 4 cookies in jar A. Divided by the probability of chocolate chips, which we found out to be 0.75. So, really mixing these up here. So 0.5 times 0.5 divided by 0.75 would be 1/3. So if we knew it was a chocolate chip, there's a 1 in 3 chance that it came from jar A. Alrighty, and that brings us to the end of the section.